You are listening to The Vocal Technologist. Spoken tech for your ears.
Get this. Hugging Face managed to parse 30,000 dense academic papers into AI-ready text for the cost of a decent espresso machine.
Wait, really? Just an espresso machine?
I mean, we are talking around $850 total, and they pulled the whole thing off in 30 hours?
That is an absolutely staggering volume of complex text to process that quickly.
Right. If you have ever tried to copy and paste text from a PDF, you know it is an absolute nightmare. You have double column layouts, weird formatting, complex math formulas, nested tables. I do not even know how you begin to extract clean text from that at volume without spending an absolute fortune on enterprise software.
Well, you cannot just throw brute force at it. To pull that off for roughly the price of a coffee machine, it takes a very specific architectural stack.
So what did they actually use?
They used a combination of serverless GPUs, which scale up instantly and, shut down the millisecond the job is done.
Yeah.
So you are not paying for idle time.
Ah, smart. So no servers just sitting there spinning.
Exactly. And they paired that with open OCR models, specifically Chandra OCR2. Then they tied the whole orchestration together using scripts generated by Codex. It literally turns 30,000 PDFs into clean markdown that an AI can actually read and understand.
So they basically glued together cheap on-demand compute with open-source vision models to bypass the expensive proprietary tools entirely. It's just wild efficiency.
It really is a masterclass in elegant constraints.
Which sets up our mission perfectly. We're looking under the hood of how companies are taking massive data pipelines and AI from these, hyped-up prototypes to robust, production-ready engineering. We are pulling apart the mechanics of true scale for time-poor professionals.
So we're getting into the actual plumbing of it all.
Spot on. Let us get right into it. Think about a standard machine learning team. If you are listening to this and work in data, you know the grind. You have data scientists dreaming up ideas, writing the boilerplate code, running the experiments, waiting around for results.
And then trying to analyze those results, yeah. It is entirely bottlenecked by human processing time.
Exactly. And that human bottleneck is what the engineering team at TEDS decided to tackle. They built a multi-agent system to orchestrate their entire machine learning experimentation lifecycle. They effectively automated the scientific method for their own model.
Which is fascinating. They completely removed the human waiting time.
Okay, let us unpack this, though. When you say multi-agent system, what are these agents actually doing? Because, well, the phrase gets thrown around heaps. Are these just basic scripts or something more autonomous?
They are essentially highly specialized AI workers interacting with each other. TEDS divided the machine learning workflow into distinct roles. So you have one agent responsible purely for generating hypotheses based on past data.
Right, the ideas person.
Yeah, exactly. It passes that idea to another agent, which actually writes the Python code. Then a third agent takes that code, provisions an isolated container in their infrastructure, and executes the experiment.
Oh, wow. So they are spinning up their own environments.
Yep. Then a final agent analyzes the logs and the performance metrics and decides what the next hypothesis should be. They pass structured JSON payloads back and forth to keep everything aligned.
I have to admit, my initial reaction to this is a mix of genuine amusement and a bit of existential dread. We are basically letting AI manage other AI now. It is properly weird. So if the agents are writing the code and doing all the actual data science, what are the human engineers doing, just watching the terminal scroll by?
That is the crucial question, right? Is a massive shift in how we work. The humans are elevated to setting the strategic direction and defining the boundaries.
So more like supervisors.
Exactly. They are managing the overarching goals and providing the guardrails, rather than writing the boilerplate code or manually tracking experiment variables in some massive spreadsheet. And the results are undeniable. TEDS saw their experiment cycle times drop from days to just hours.
That is a huge jump in velocity.
It is. The volume of meaningful experiments they could run went up 4.5 times. And most importantly, because they can test so many variations, the performance of their production models improved by 8 to 12%.
It makes complete sense. If you can test 100 ideas in the time it used to take to test 5, your final product is going to be sharper.
But hang on, surely it is not just magic. There has to be a catch when you leave AI agents running continuously in a loop like that. They do not just run flawlessly forever.
Oh, there absolutely is a catch. And it is a really fascinating technical hurdle. The engineering team at Slack wrote a brilliant piece highlighting exactly this issue. They call it context rot.
Context rot. That sounds like what happens when I leave 50 browser tabs open and totally forget what I was researching in the first place.
It is actually a very accurate way to think about it. When you have these long-running agents, they are constantly taking in new information, executing tasks, observing the results. But underlying language models use what is called an attention mechanism, and they have fixed context windows. Right, they can only hold so much in their working memory.
Precisely. As that window fills up with new tokens, the model's mathematical attention gets spread too thin. If you just force-feed them more information or rely on a simple database search to fetch past actions, the agents start to lose track of important earlier instructions.
So the new stuff just overwrites the old stuff.
Basically, yeah.
Yeah.
The mathematical weights of the new information drown out the old facts. They literally forget why they made a decision 3 hours ago. The context just rots away.
So how do we actually fix that? Because if these agents are going to be acting like middle management for our data pipelines, they need to reliably remember what happened yesterday. We cannot have an automated workforce with severe amnesia.
We have to stop treating AI memory like a simple text search database. A reliable AI memory system needs to actively manage decay, contradiction, and expiry.
Actively manage it. So not just a dump of files.
Right. To solve this, researchers and teams like the one at Slack are moving towards a SQLite-based design for agent memory, keeping the memory local and structured.
But how does putting it in a local SQLite database actually solve the rot? Storage is just storage, surely.
It is not about the storage mechanism itself.
Oh.
It is about the computational logic applied to that storage. Instead of just dumping plain text memories into a giant vector database, you store them locally and run a continuous background process to score them.
Ah, I see. Scoring them based on what?
You calculate a score for every memory based on its importance, its confidence level, and a mathematical decay curve over time. This means outdated facts or weakly supported beliefs naturally fade away and stop dominating the retrieval process.
Okay, so when the agent pulls up its memory, new, highly confident memories have logically superseded the older, less relevant ones.
Exactly.
Right. It is exactly like sitting at a crowded pub table. Eventually, you have to actively clear the empty glasses so you have room to put down the new drinks. If you just keep stacking them higher and higher without clearing the table, the whole thing collapses and you cannot even find your own pint.
That is a spot-on analogy. The agent periodically reviews its own history, merges duplicate beliefs into higher signal summaries, and clears the table. But there is a crucial security warning here regarding agent harnesses.
Oh, what kind of warning?
If you use a closed, API-based harness to run your agents, you are surrendering control of how that memory scoring and storage is managed. You do not truly own your agent's memory or its internal logic.
Which is a massive risk for any enterprise handling sensitive data.
Absolutely massive.
Which, yeah, is exactly as terrifying as it sounds. Outsourcing the very memory and reasoning of your automated workforce to a third-party box you cannot look inside. But speaking of things collapsing under pressure, those AI memory systems creating constant local updates put an unbearable write load on the underlying infrastructure.
Yeah, they really do.
Which perfectly explains the physical wall that companies hit when moving raw data around. The unsexy reality of all this AI advancement is that someone has to physically move the data without the servers catching fire.
And very few operations move data, quite like Airbnb. They faced a monumental challenge migrating their massive metrics pipeline from a legacy Stats-D system to OpenTelemetry and Prometheus.
We are talking about a huge volume of data there.
Massive. We are talking about an environment where they ingest over 100 million metric samples every single second.
100 million samples a second. I cannot even conceptualize that. How does a software system handle that volume of traffic without the network cards just melting or the application giving up entirely?
Well, initially, the application did struggle severely. When they rolled out a dual write strategy to transition their highest volume services, they hit massive memory and garbage collection regressions.
Okay, unpack garbage collection for me in this context. Why does that cause a regression?
So in programming languages like Go or Java, memory allocation requires active management. When a metric comes in, the program creates an object in the server's RAM. When it is done processing, a background process called the garbage collector has to pause the application.
Just freeze everything.
Yes, it pauses it, scans the RAM, and sweeps away the unused objects to free up space. But at 100 million objects a second, those required pauses become so frequent and so long that the program spends more time cleaning its own memory than actually processing the incoming data. Performance degrades to a crawl.
Ah, so the system chokes on its own exhaust. It takes too much compute just to throw out the trash. How did they solve it without just buying 1,000 more servers?
They implemented a highly specific two-part engineering solution. First, they switched select high-volume workloads to delta temporality.
Delta temporality. So rather than a service sending the whole absolute data set over and over, are they just sending the mathematical difference? Like an accountant only updating the changing margins on a ledger rather than rewriting the entire book every 5 minutes.
That is exactly right. Instead of a server saying, I have processed 1,000 requests, then a second later saying, I have processed 1,005 requests, it only sends the change. It just broadcasts, hey, I processed 5 new requests.
Oh, that makes sense. That would save a ton of bandwidth.
It dramatically reduces the memory footprint required to track the state across the network. And second, they implemented a two-layer vMagent aggregation tier.
What is a vMagent and how does layering it help?
Think of a vMagent like a local post office. Instead of every single house sending a letter directly to the central sorting facility and overwhelming it, the vMagent sits at the edge of the network. It collects the thousands of metric samples locally, does the mathematical aggregation right there, and then only sends the final, neatly packaged sums to the central storage.
So they do the heavy lifting before it even hits the center?
Exactly. Layering these allowed Airbnb to scale out hundreds of these local post offices, preventing the central database from collapsing.
It is all about graceful degradation and managing the flow at the edge, which is a principle Yelp clearly understands too. They pulled off what sounds like an IT miracle, upgrading over 1,000 Cassandra database nodes from version 3.11 to 4.1 across multiple clusters.
With zero downtime.
Right, zero downtime, no dropped requests.
Achieving zero downtime on a stateful database upgrade of that physical scale is an incredible engineering feat. Cassandra is heavily reliant on a gossip protocol.
Gossip protocol, meaning they're constantly talking to each other.
Right, peer-to-peer communication between nodes is constant. When you have older nodes running one version, trying to synchronize data with newer nodes running a different version during a rolling upgrade, the cluster state can corrupt very quickly.
So how do you manage 1,000 different servers gossiping with each other without a single dropped request during the flip?
It requires extreme orchestration, specifically using Kubernetes init containers.
An init container, is that like a pre-flight check before the main application runs?
Exactly. You can think of an init container like a bouncer at a nightclub.
I love that, a digital bouncer.
Yeah. Before the main Cassandra database process is even allowed to start and open its doors to live traffic, the init container runs a strict checklist. It ensures the new database node is perfectly synced with the older network, checks the schema versions, and validates the gossip protocols.
So it does not let anyone in until the room is ready.
They implemented incredibly strict monitoring during this mixed version period, ensuring that older nodes could still comprehend the binary data being written by the newer nodes. Only when the bouncer verifies everything is safe does the new node join the cluster.
And the payoff for that meticulous bouncer logic was huge. They saw overall latency improvements between 21 and 60% just from getting the underlying database engine cleanly upgraded. But let us look at a database frustration that is probably a bit more relatable for anyone listening. Postgres job queues. Every time I see an engineering team try to use standard Postgres as a high-throughput job queue, it eventually degrades and grinds to an absolute halt.
It is an incredibly common architectural trap. What is fascinating here is that the degradation is rarely an actual computational limit of Postgres itself. It is almost always a mechanical issue with dead tuples.
Dead tuples, which honestly sounds like a terrible punk band. What is actually happening under the hood there? Why are they dead?
Well, Postgres uses a system called multi-version concurrency control to handle simultaneous reads and writes. When you delete a row, say a background job is finished and you remove it from the queue, Postgres does not actually wipe the data from the hard drive immediately.
Wait, it does not delete it?
No, it just marks it as dead, making it invisible to new queries. This invisible row is a dead tuple. A separate background process called vacuuming comes along later to actually sweep the drive and reclaim the physical space.
I see where this is going. If you are churning through tens of thousands of automated jobs a minute, you are instantly creating tens of thousands of dead tuples.
Exactly. And the real mechanical problem occurs when long-running analytical queries from other parts of your business are holding open transactions.
Oh, no.
Yeah. Postgres is designed to be safe. It will not vacuum those dead tuples if there's any active query anywhere in the system that might theoretically need to look at them. So the dead tuples pile up. The database engine has to physically scan past all this invisible garbage on the disk just to find the 5 active jobs you actually want.
So the hidden overhead just grows exponentially.
And the whole system slows down.
It is literally like trying to mop a busy cafe floor while people are still walking across it. You cannot actually clean the floor. You just end up pushing the muddy water around while more people track in dirt until the whole cafe comes to a complete standstill. To actually clean it, you have to temporarily stop the foot traffic.
That is the exact dynamic. You have to implement strict controls to limit the competing query traffic so the vacuuming process can actually lock the rows and run effectively. It is never about throwing more RAM at the database. It is about understanding the physical, mechanical limitations of the cleanup process.
Which naturally brings us to how we actually store and index all this data without going bankrupt.
Oh.
Let us move from operations to the data lakehouse. Pinterest handles an astronomical amount of user interaction data for their recommendations, and they are using Apache Iceberg to manage it at scale.
To efficiently scale their machine learning pipelines, Pinterest introduced request-level deduplication. They sorted their raw data by user ID combined with a request ID directly inside Apache Iceberg. This allowed for massive storage compression because they only store and process the highly specific request-level data once per unique interaction, rather than duplicating it across multiple tables.
If you are working in data, you hear Apache Iceberg mentioned constantly. But how does it actually work? How does it make a disparate pile of data files sitting in cloud storage behave like a cohesive transactional database?
Iceberg achieves this through a very specific three-layer architecture.
Yeah.
First, you have the data layer. This is just the actual Parquet file sitting in your object storage, holding the raw compressed data.
Just the dumb storage file.
Exactly. Second, you have the metadata layer. These are immutable tracking files that document the schema, the specific data partitioning, and the snapshot history. They dictate exactly which data files belong to which version of the table.
So the metadata layer is essentially a hyper-detailed map of where every single byte lives.
Precisely. And finally, you have the most crucial part, the catalog layer. This layer manages the atomic commits. It holds a single authoritative pointer to the current active metadata file.
Ah, so that is the source of truth.
Right. When you write new data, you create new Parquet files, you write a brand new metadata file, and then you update the catalog pointer in one atomic swap. It uses optimistic concurrency control to verify no one else changed the table while you were writing.
That is how you get safe, guaranteed transactions without locking up the entire massive database.
Exactly.
That is a brilliant mechanism, but there is a massive shift happening right now with how we handle that specific catalog layer. We are seeing tools like Duck Lake reaching version 1.0, and they point out a fairly major architectural flaw in how traditional lakehouses have handled this index.
Yeah, traditional table formats often store those crucial catalog and metadata files as flat JSON or Avro text files directly in object storage buckets like AWS S3.
Which, every time I think about it, completely blows my mind. We are building these hyper-advanced AI pipelines, dealing with millions of records a second, and the core index for our massive distributed systems is basically just a huge stack of plain text files sitting in a cloud bucket. It seems wildly inefficient.
It creates a tremendous computational bottleneck. Reading, parsing, and verifying thousands of flat text files over a network just to plan a single query is incredibly slow.
So how does Duck Lake fix that?
Duck Lake version 1.0 fixes this by keeping all the metadata in a real database catalog. They use embedded database engines like SQLite or DuckDB itself to physically store the metadata.
Oh, it makes so much sense.
It makes the Lakehouse behave mechanically like a regular database,
Yeah.
drastically speeding up query planning because you are querying in an index, not parsing text files.
Put the index in something that was actually engineered to be queried. But here's the thing. We can have the most elegant lakehouse architecture in the world with embedded catalogs and atomic swaps. But if the actual data flowing through it is garbage, the whole system is entirely useless. And traditional schema validation is letting a lot of dangerous garbage slip through undetected.
This is a vital point about information integrity. As an industry, we rely heavily on basic structural checks. Does this column contain null values? Is the row count what we mathematically expect?
Is it an integer when it should be an integer? That sort of thing.
Exactly. But these basic checks completely miss silent information loss, or what we call distribution collapse.
Okay, give me a real-world example of distribution collapse, because it sounds fatal to a machine learning model.
Imagine you have an industrial pipeline processing thousands of temperature readings from factory sensors. The schema validation says it expects a floating point number. The row count matches yesterday's volume perfectly.
Everything looks green.
Right. But because of a subtle logic bug introduced in a Python transformation step upstream, Every single sensor reading is suddenly recorded as precisely 22.5 degrees.
Oh, I see.
The schema validation passes, the row count passes, the pipeline shows green across the board, but the variance, the actual physical meaning and utility of the data, is completely destroyed.
The dashboard says everything's perfectly fine, but the actual information is completely gone. If standard tools are entirely blind to that, how do we actually catch it before it poisons the model?
By borrowing a concept from physics and information theory called Shannon entropy.
Shannon entropy. Okay, what is that?
Shannon entropy mathematically measures the amount of unpredictability or actual information content in a signal. If you monitor the Shannon entropy of that temperature column and it suddenly drops to near zero, it means the data has lost its variance.
That is brilliant.
It acts as a highly sensitive signal integrity metric to catch the silent structural failures that simple row counts completely miss.
Using pure physics to monitor software data pipelines. I absolutely love that. But it brings up a huge frustration for me. If we have access to all these incredibly smart, elegant solutions, Shannon entropy, Duck Lake catalogs, multi-agent orchestrators, why do enterprise data tools still feel so incredibly bloated, slow, and difficult to use?
It fundamentally comes down to the underlying economics of the database industry. It is a concept we call the ops tax.
Explain the ops tax, because on paper, database vendors look like they print money. Their gross margins are always insanely high.
They do have high gross margins, but their research and development, and crucially, their massive sales and go-to-market costs are astronomical. Building a reliable distributed database takes years of highly specialized engineering. But their real existential threat comes from the massive cloud providers, the hyperscalers. If an independent database vendor makes their product too simple and too easy to run, a cloud provider will just fork the open source version, host it on their own infrastructure, and steal the entire market overnight.
Right. So the vendors are forced to build a moat to defend their margins. How do they actually do that technically?
By intentionally adding operational complexity.
Wow, on purpose.
Yeah. They differentiate themselves by building highly specific proprietary features. They create complex operational and administrative requirements that only their expensive enterprise support teams can properly manage.
So the net effect for the data engineer trying to build a pipeline is that software products constantly get more features, but they never ever get simpler to operate.
The complexity itself becomes the economic moat to preserve the vendor's survival.
That is a fairly bleak reality if you are an engineer just trying to build something that works. But thankfully, the open source community is pushing back incredibly hard against that bloat. We are seeing a massive surge of lightweight, extremely sharp tools that solve specific problems without demanding a massive enterprise contract.
The contrast in the engineering philosophy is stark. Instead of buying a massive monolithic platform, developers are reaching for highly focused, performant utilities.
Take a tool like Kuva, for example. It is a plotting library built entirely in Rust. It takes raw CSV or TSV data and turns it into beautiful publication-style visuals incredibly fast, and it does it without requiring you to haul in a massive, heavy Python plotting stack and manage endless dependencies. You just run it straight from the command line.
Which is so much cleaner.
Or look at Doclo. It is an open-source tool that takes standard DBT projects and instantly turns them into clean, interactive documentation with data lineage and an AI chat interface built right in. It is a lightweight, instant alternative to buying a massive, clunky enterprise data catalog.
And we are seeing this exact same lightweight, highly intelligent approach transition into the AI space with tools like Protocol H.
Yes, Protocol H is fascinating. It is an open-source retrieval augmented generation framework, but it completely abandons the standard flat agent model we usually see. It uses a strict hierarchical supervisor-worker architecture.
Which is absolutely crucial for complex reasoning tasks.
Okay.
In a standard flat model, one single agent tries to plan the query, fetch the data, and write the answer all by itself.
And it usually just falls over.
Right, it often gets confused or hallucinates. Protocol H uses a deterministic orchestrator. The supervisor agent breaks down a complex query, delegates the SQL code generation to one specific worker, delegates the vector database search to a completely different worker, and then synthesizes the final result.
So it divides and conquers.
It significantly outperforms standard systems because it applies structured software engineering principles to the AI routing.
Which brilliantly brings this entire discussion full circle, whether we're talking about multi-agent systems orchestrating experiments or open source frameworks using supervisor architectures, or even something as purely mechanical as the new Polar's data manipulation library.
Yes, Polar's recently implemented streaming sort merge joins,
Right.
which physically drops the need to build memory-intensive hash tables when the data keys are presorted, cutting processing time by up to 18 times.
Exactly. It all proves that true sustainable scale is not about brute force. It is not about throwing more expensive servers or more enterprise bloat at a problem. It is about elegant constraints.
Spot on.
It is about designing systems that logically manage their own memory, that gracefully degrade under extreme network pressure rather than crashing, and that treat data integrity as a measurable physical property.
Elegance and strict architectural constraints are the only ways these massive systems remain manageable as the sheer volume of data continues to explode.
But all of this does leave me with a question that I cannot quite shake. As our AI agents develop their own persistent memories and complex multi-agent social structures, and as our underlying databases rely on increasingly intricate, multi-layered architectures just to stay functional under the load, are we rapidly approaching a point where we are building automated data pipelines that are simply too intricate for any single human engineer to ever successfully debug? I want you to chew on that. And as always, keep questioning the tech you rely on. This is Vocal Technologist, signing off.
Spoken Tech for your ears.